Our next topic is a big topic. It's continuity. The reason it's such a big deal is if a function does not have the property of continuity, then roughly speaking, the techniques we're going to develop this semester don't work. Very roughly speaking, in a very rough cut, if the function is not continuous, if it does not have continuity, then roughly speaking, the calculus doesn't work. So we want to make sure it does have this property. Continuity is one of those things, sometimes it's easier to describe something by describing what it is not. And so these are examples of a function that is not continuous. A function is not continuous. Now we talk about continuity. It is continuous. It has continuity at x equals c. All right, so let's suppose x equals c. So here's c. A function can fail to be continuous several ways. One way is this. A function might have a hole in the graph at x equals c. Right? This is a discontinuity. It is a discontinuity. It is discontinuous. If you don't like discontinuous, you can say it's not continuous at x equals c. That's one possibility. Now, a subcategory. It is still this category. It's a subcategory. Would look something like this. There's a hole here, but the function value is filled up here. So that would, there are certain weird looking kinds of functions where this can happen. For our perspective, all we're saying is, now in this case, let's suppose this number is 4. Let's suppose this number is 6. So this is 4, this is 6. So what is f of c in this case? What is f of c? F of c, the function value is 6. So the function is defined. It does have a dot there. But what is this value? This is the limit. The limit is 4, because as you get closer and closer to c, remember, closer and closer but not equal to c, you're getting closer and closer to 4. As soon as you hit c, then we have left the limit. Remember, the limit, we don't care what happens at x equals c. So at x equals c, we leave the limit behind. Now we do the function value. And so if there's a separate point above or below, that's like a subcategory of this type of discontinuity. All right? This kind of discontinuity has a name. It's called removable. I think that's how you spell removable. It's removable. We could remove the discontinuity by redefining a single point. You could just redefine the function at a single point and it would be continuous. So that's why this is called removable, is because you could remove it by one point, by redefining the function at one individual point. It's a removable discontinuity. Right? There's another kind of thing that can go wrong with continuity. Something like this. Here's my value of c. These piecewise defined functions. This function is defined piecewise. And so here the function jumps. Sometimes in engineering or in applications or in some places in finance or demographics, you have things called interruption events. And when an interruption event occurs, very often you'll have this sort of behavior in the graph of the function that you're playing with. And so there's this kind of discontinuity. There is a discontinuity, it is discontinuous at C. This has a name, it's called a jump. It's called a jump discontinuity. Notice, Look at the two pieces. What's f of x, or f of c? The function value at c actually is defined. It's right here. Here's f of c. So there's no problem defining f of c. But what is the limit? All right, let's call this P. Let's call this Q. Well, the limit is not P, because if I form my delta interval, these values don't get, here's my epsilon interval, there's my delta interval. These values don't get inside the epsilon interval. So P is not the limit. And if you form an epsilon interval around Q, then for my delta interval, these guys don't get inside the value of Q, these function values. And so it's not P, it's not Q. It can be shown there is no function value, so this limit does not exist. So in a jump discontinuity, the function might be defined, but the limit doesn't exist. So this is, when we're talking about, if we want the function to, yes, be continuous, that means we don't want that and we don't want that. There's one more thing we don't want. We don't want a vertical asymptote. If there is a vertical asymptote at C, the function is not continuous. Now, is it clear? If there's a vertical asymptote, f of C does not exist. And if there's a vertical asymptote, the limit does not exist. Neither the function nor the limit exists here. So, if we want to have a function that is continuous, and for our purposes, we need to have continuity happening. So if we want to have a function that is continuous, it does have continuity. That means we do not want this, and we do not want this, and we do not want that. All right? I'll say this over and over and over and over going forward. If I in Calc 2, I say it over and over again. Calc 3, over and over and over again. If a function is continuous, what does that mean? That means no holes, no jumps, no vertical asymptotes. If the function is continuous on an interval, has no holes, no jumps, no vertical asymptotes. No holes, no jumps, no vertical asymptotes. So, we put that all together. This is the nuts and bolts. Those what we just looked at, those were the big ideas. Here are the nuts and bolts. A function f of x is continuous at x equals c if a function is continuous, there are three conditions to be met. For now, if I ask you what are the three, not if, when I ask you what are the three conditions required for continuity, you do not go writing some paragraph of, well, it's got to look like this and the graph, no. If the question is, what are the three requirements for a function to be continuous? What is required for a function to be continuous at a point? You need to write 1, write this, 2, write that, 3, write that. Number 1, the first thing that requires is f of c is defined. And when we say defined, we are not allowing infinity. So the function is defined. It is a finite number. When you plug c into the function, you actually do get an answer. Number 2, the limit as x approaches c of f of x is defined. And number 3, the limit as x approaches c of f of x and f of c are equal to each other. The function must exist, the limit must exist, and the answer you got from number 1 and the answer you got from number 2, they must equal each other. If you do this and you get 5, wonderful, so far so good. If you do this and you get 4, wonderful, so far so good. But 4 does not equal 5, so you would say this function is not continuous at C. Now let me show you what's going on. Remember the hole? If there's a hole, you're violating this requirement. You're saying, okay, what if there's a point up here? If there's a point up there, yes. Now the function is defined. The function is defined to be 6. The limit is defined. The limit is defined to be 4. However, 4 and 6 are not equal, so this fails to be continuous. Okay, what about a jump? The function is defined. Yes, it's defined right here. The limit, oh no, the limit is not defined because the top and the limit is not defined. So this would fail condition number 2. This fails condition number 2. Technically number 3 also, but fails condition number 2. As soon as it fails condition 2, you stop. If it fails condition 1, there's no need to check the others because it's all or nothing. All right? And then this explains why vertical asymptote is not continuous. Because what is f of c? F of c has got to be a finite number. This f of c is not defined. And so for that picture, condition number 1 fails. The function is not defined at c. Or the function is not defined, therefore it's not continuous at c. So, in order for a function to be continuous, each of those properties must hold. So let's do one more thing here. Show that f of x equals x squared minus x is continuous at x equal, and just pick a number out of the blue sky, x equal 4. I want to show that function is continuous at that value. In this problem, c is equal to 4. So, if you're going to show a function is continuous, you need, at a point, you need to show those 3 properties hold. Number 1. Do you get an answer? I don't care what it is, just do you get an answer? Well, that's 4 squared minus 4 is 12. Ding! Condition 1 has been met. Number 2. What is the limit? Do you get an answer for the limit? What is the limit as x approaches 4 of my function, which is x squared minus 4? Well, plug and chug, that's 4 squared minus 4, which is still 12. Ding! So, condition number 2 has been met. And then number 3. 4, all right, let's say it this way. The limit as x approaches 4 of x squared minus x is equal to the function value. Yes, 12 is equal to 12. Ding! And so we can say, therefore, show the function is continuous there. Therefore, the function is continuous. Therefore, it is continuous at x equals 4. So these are the 3 requirements for a function to be continuous at x equals 4 at a single point. Continuity at a point is determined by these 3 properties.